Hello and Assalamualaikum. So today my group will be presenting about experiment 1, which is the Bernoulli's principle. So these are our group members. So the Bernoulli's principle is a fundamental concept in fluid dynamics that explains how the speed, pressure and potential energy in a moving fluid are related. Named after the Swiss mathematician Daniel Bernoulli, the principle states that as the velocity of a fluid increases, the pressure decreases, assuming that the flow of the fluid is steady, incompressible and frictionless. So the objective of the experiment is to measure and calculate fluid flow velocities in the venturi nozzle at different points. And the second objective is to investigate the static, total, and dynamic head distribution along the venturi nozzle. The third one is to determine the flow coefficient at different flow rate. And the scope for this experiment is the volume of water collected is 2 liter.
For the theory part, the Bernoulli equation shows that for a fluid with constant density, and when we consider the friction losses, we change the pressure P1 and P2 to static heads. So based on the new equation, H represents static head, W is the fluid velocity, and H loss is energy loss due to friction. In a closed system, mass flow rate is conserved, meaning M1 is equals to M2. Given that V is equals to A times flow velocity, the velocity changes with area in a pipe, but flow rate remains constant. At 6 points in the nozzle, the velocity is calculated based on a standardized reference velocity. The nozzle flow coefficient Kv relates pressure drop to flow rate, helping determine flow through the nozzle. The nozzle flow coefficient Kv relates pressure drop to flow rate, helping determine flow through the nozzle.
So these are the experimental setup and the apparatus that we use in the experiment. We have the white valve, the info panel, the water inlet, ventometer, main switch, pump switch, black valve, 7-tube manometer, measuring probe, control outlet valve, volume of water collected, and the stopwatch. The first step for the experiment is to switch on the main switch and the pump. And then we have to control the outlet valve slowly until the maximum level to eliminate air in the system. And then the black cap valve will be controlled slowly in order to eliminate the air bubbles inside the manometer. After the system is stable, the outlet valve and the pump are turned off. And then the white valve is opened slowly until it reaches 80 out to 100 millimeter, and the pump is switched on and the outlet valve is controlled until the manometer level P1 reaches its maximum and P3 reaches its minimum. The reading at the manometer for P static are collected for all the data, which is P1, P2, P3, P4, P5 and P6. And then the measuring probe is put simultaneously parallel under the manometer tube to obtain the reading of P total. The reading are collected from the last manometer in the system. And then the volume of the water collected at the tank will be recorded with the time, and the outlet valve is adjusted by reducing the flow to obtain other readings, and then step 7 to 10 are repeated.
Is the result for our experiment. So we collected 2 liters of water, and then we record the time. So we obtain Q actual by dividing volume of the water with time, and we record P static and P total, and P dynamic by subtracting P total with the P static.
Next, we will see discussions. The first question asks us to calculate fluid flow velocities. We calculated theoretical and experimental velocity and also its percentage error. So how did we calculate? We calculated the theoretical value. First, we convert unit for volume of water to meter cube, then calculated the volumetric flow rate, which is by volume of water divided by time, and finally by using the formula from theory part, we have calculated the theoretical velocity. Here I have shown the calculation for experimental velocity, which is by using the formula square root of 2 times gravitational acceleration times dynamic head. Then I have calculated percentage error by using the formula theoretical value minus experimental divided by theoretical and times with 100%. Theoretical velocities for other pipe sections have been tabulated. As you can see, the smallest pipe diameter P3 has the highest velocity. This is due to as area of pipe section increases, velocity decreases, pressure increases, and time for water flow increases. This table shows the values for experimental velocity. We have used the formula velocity equals to square root of 2 times gravitational acceleration times with a dynamic water column height to calculate the experimental value. Then we have calculated percentage error. The formula used is theoretical value minus experimental divided by theoretical value times 100%. From the table, we can see that there are errors during experiment. Errors such as parallax when reading the water column height, formation of unnoticed bubble, or might be even due to our assumption which is major and minor losses are equals to 0. From the table, we also can see that the highest error we got is 90.6 percentage and the lowest is 0.84 percentage. The second question asked us to calculate and discuss static, total, and dynamic heads. So we have calculated for the first data as shown in the table. For other results, we have shown in the previous section, which is in results table. We have plotted a graph of length of pipe section versus H values. We can see three different trends here. First is total head, which the graph shows like a line. Static head shows a trend of decreasing and falls to minimum value before increasing, but did not reach the same value as initial. Dynamic head increases to a maximum point and then decreases. As for the total head, why the graph looks like line? Because head pressure is the sum of static head and dynamic head. The total head value will be constant because according to the principle of conservation of energy, it states that the energy cannot be created or destroyed. That's why the energy in the Venturi nozzle remains constant, but it can be transformed into another form of energy, which is potential energy and kinetic energy. Next is static head. The reason why the graph shows decreasing trend is that when the area of pipe decreases, the fluid velocity increases. Static pressure is converted into kinetic energy to make the fluid move faster. That's why the static pressure decreases. So the lowest part of the graph shows that the fluid moves through the narrowest part of the nozzle. So it consumes high amount of kinetic energy and the static pressure drops. Then pressure increases back as the area increases, but did not reach its initial value due to energy losses. And finally, the dynamic head. At initial, it shows an increasing trend. This is due to the pressure. As fluid flows into the narrowest part of the pipe, the velocity increases and pressure increases and reaches the maximum dynamic pressure. As the pipe section becomes larger again, the velocity decreases, causing pressure to also decrease. The third question asked us to calculate flow coefficient at different flow rates. So we use the formula flow coefficient equals to volumetric flow rate divided by square root of gravitational acceleration and times with difference in largest dynamic head and lowest dynamic head. The results of the calculation have been tabulated in the table. From the table, we can see that the relationship, the smaller the volumetric flow rate, the smaller the flow coefficient value.
One is the safety precaution. So the first one is to ensure there is no bubbles in manometer because it will affect the pressure reading. Second one, ensure eyes are perpendicular to the meniscus of water in the manometer. Third one, slowly open the white valve until it reaches 80 to 100 millimeter. We can conclude that in this experiment, fluid flows through a tube that narrows in the middle. As it passes through the narrow part, it speeds up, which causes the pressure to drop, while when it moves back to the wider part, it slows down and the pressure goes back up. This experiment shows in a fluid velocity are inversely proportional to pressure.
So these are all the references that we use in this experiment. Thank you.